Okay, in this video we're going to have a close look at fields. Now this won't be entirely comprehensive, but I'm going to study the following topics that are listed out here and a few more. Okay, so a field is a commutative ring with a 0 and a 1, which are the additive identity and the multiplicative identity, in which every non-zero element has a multiplicative inverse. Now, a field is also a ring, except we don't require that every element of a ring has a multiplicative inverse. So it's not just a ring, it's a commutative ring, meaning that A times B has to be equal to B times A in your field in order to be a field. Okay, so we're going to go over these examples of fields, and then we're going to look at finite fields. And so just briefly show you what's on the page for the summary or the overview of what we're going to look at in terms of finite fields. Okay, but back to these characteristic zero fields first. So these examples are rational numbers, real numbers, complex numbers. The extension rational numbers adjoin the square root of 5 is another example of a field. This is an extension of the field of rational numbers. This field, in which we have the square root of 2 and the square root of 3 in our field, this is an extension of the rational numbers. And this field here is the field obtained by adjoining the cube root of 2 to the rational numbers. And so this is an extension of the rational numbers. Now, these fields are all examples of fields of characteristic 0. Okay, and what that means is that if you take your multiplicative identity and you add it to itself n times, and you get the additive identity from doing that, and this implies that n is equal to 0, then you have characteristic 0. Okay, so these fields have characteristic 0, but the finite fields over here have characteristic p, where p is a prime. Okay, we're not going to have a field unless our characteristic is prime in the case of a finite field there. Okay, so next we're going to look at field extensions, and briefly, because there's a lot in this topic, briefly the Galwa correspondence, which I've just got drawn here, but we'll refer to this in a bit more detail soon. And we're going to look at, again briefly, the fundamental theorem of Galwa theory. Okay, so I've got it set out here, but we'll talk about it more soon. Okay, and after that, we are going to look at finite fields. So, for example, integers modulo 3, because 3 is prime, every element of that field is invertible other than 0, as in has a multiplicative inverse. So that forms a field. Integers mod 2 cross integers mod 2, or the Cartesian product of integers mod 2. That's a finite field of order 4. And then f modulo, or integers modulo p to the power of n, where n is greater than 1. This is another example of a finite field. And in fact, this, together with multiplication, when you exclude 0, that is a cyclic group, and we know that there's only one of these up to isomorphism, meaning that if two are isomorphic, then we treat them as the same. Okay, and then some other topics on finite fields, including the Frobenius Automorphism. So that's what we're going to look at in this session here. Okay, so moving on, let's talk about our first example of a field. Okay, and I'm just going to bring this over here so we have a better view of this. Okay, the field of rational numbers. So this is equal to the set of all A over B, where B is non-zero, and A and B are integers, and you can assume without any loss of generality that they're reduced. The fractions are reduced, meaning that the GCD of A and B is equal to 1, but you don't have to here. Okay, so this is our set. Now we know that Q together with addition is an abelian group. Okay, and we've talked about this in our previous sessions on groups and rings. We also know that Q with multiplication, and we exclude 0, so we throw away 0 in this operation. This is an abelian group. Okay, just meaning commutative. The operation is commutative, AB equals BA. Is what abelian means there. Okay, we also know from our previous session that this is a commutative ring, right? Because we have commutativity of multiplication, so that makes this a commutative ring, right? And remember what we required to make that a ring is that this is an abelian group. This structure here is well defined, has a multiplicative identity, and that identity in this and in this structure, multiplication distributes over addition, right? So that would make this a commutative ring when this structure commutes, right? Now, to have a commutative ring, you don't require that this structure is a group, right? You don't have to have that every element has an inverse, right, in order to have a commutative ring, right? But we do have the fact that this is an abelian group when we have multiplication of non-zero rational numbers. And so this structure here is a field, right? Since every A over B that's not equal to 0, where B is non-zero, has an inverse. And here this inverse, multiplicative inverse, is B over A, right? Because we've excluded 0 for A. And so this is non-zero. And A is non-zero, so that is, in fact, belongs to the non-zero rational numbers. Okay, so every element in the rational numbers that is not zero has a multiplicative inverse, and so this makes this structure a field. Okay, so for the real numbers, this is basically the set of all A such that between any two real numbers, there's another real number. So I'll just describe this geometrically as the number line. okay, because it's a bit involved to describe this set without this geometric notion here. Okay, now every non-zero element of the set of real numbers has an inverse. So we'll just say the multiplicative inverse of A is equal to 1 over A, right? If A is non-zero. And so real numbers excluding 0 together with multiplication form an abelian group. Okay, and this, actually I didn't need to exclude 0 there. So actually I'll just cross that out. This is a commutative ring. Okay, we have AB plus C is equal to AB plus AC, where A, B, and C are real numbers, and the other way around also. And since multiplication is commutative, this is AB plus AC as well. Okay. So we have a field out of this because in addition to these, every element of the non-zero real numbers has a multiplicative inverse. So this is a field also. Okay, so next let's move on to some field extensions. So now we'll talk about the complex numbers. Okay, so the complex numbers form a field. Now this is equal to the set of all A plus BI, such that A and B are real numbers, and I squared plus 1 is equal to 0. In other words, I is equal to the square root of minus 1. Okay, so this forms a field, and when you have A and B, you can represent them geometrically, right? So I'll just give you an example. So this would be the real part of the complex number Z, and this up here would be the imaginary part, which would be the part next to the I. Okay, so for example, if we put Z equals A plus BI, then this would refer to the real part having A, value A, and the imaginary part having value B. And so we can think of this as the point. Okay, so this corresponds to the point A comma B. And also there's a vector here, right? So we can think of the vector AB, and I'll write this vertically. Okay, so we've described this geometrically now, but there's also a field extension here. So right, so we have an extension of the real numbers because the A and the B belong to the real numbers, and this is also a vector space with underlying field R, because remember, when you have a vector space, you need to talk about it in terms of its underlying field. Okay, so what I'm trying to say here is that the vectors A, B have A and B belonging to the real numbers here. When you think of the complex numbers as a vector space. Okay, now the degree of this extension, and so let's use the notation square bracket colon, separating the extension there and the base field there. The degree of this extension is essentially how many, or the degree of that polynomial that I require there to describe this number I. Okay, and so now there's a corresponding Galwa group here, meaning the group of all automorphisms of this field. So we'll say Galwa group of the extension this is isomorphic to the group containing the identity, and here I'm just going to use the Greek letter iota for that, and then we'll have, say, phi, where phi maps I to minus I, right, and minus I to I. Okay, now this is an automorphism because it's just a permutation of the elements of the complex numbers such that a plus bi would get sent to a minus bi, and a minus bi would get sent to a plus bi. So we've just permuted the elements of the complex numbers. But what it does is it leaves this base field real numbers, it leaves that fixed because the real number a gets sent to the real number a, and so it's fixed by this automorphism of the field. Now an automorphism is an isomorphism of the field to itself. Right, so essentially you have two fields that are algebraically the same. Okay. Next, let's have a look at the rational numbers adjoin the square root of 5. So I've already described the ring. So I'll say already described the ring Q square bracket root 5. Okay, which if you go back and look at my previous video there, that consists of the elements a plus b root 5, where a and b belong to rational numbers. But here we talk about it as a ring. Okay, so we put the square bracket there, but this one is essentially the same thing. It just happens to be a field. So A and B belong to the underlying field Q. And we know here that root 5 squared is equal to 5, and so that is rational, and so we don't need to keep going with this and represent root 5 squared and root 5 cubed and so on, because we only end up with elements of this form. Okay, so this is also a field because we've already said that we have this as a ring, so multiplication distributes over addition. The number 1 is a multiplicative identity in that ring, but every element has an inverse. So we'll say also every a plus b root 5 has an inverse, and by inverse I mean multiplicative inverse. So that inverse would be a plus b root 5 to the power of minus 1, and this is truly a power here because this is a plus 1 over a plus b root 5. Okay, and so I'll just show you that this is actually in this original set, because what I can do is multiply here by the, actually I should say every non-zero, right? Every non-zero element, because I forgot about that here. Okay, every non-zero element, a plus b root 5, has an inverse of this form, and I'll just show you that it's actually can be represented as a plus b root 5, where a and b are rational numbers, because what I can do is multiply on top and bottom by the algebraic conjugate, which is a minus b root 5. So multiplying top and bottom by a minus b root 5. Okay, I down here have the product a plus b root 5 times a minus b root 5. Okay, now expanding that denominator. So in the numerator we still have a minus b root 5, but in the denominator we have a squared, and then we have plus ab root 5, and then we have minus ab root 5, and then we have minus b squared root 5 squared, but that's just 5. Okay, so in other words, we see these two vanish, right? Their difference is 0. And so we have basically now in the denominator a squared minus 5b squared. But a squared minus 5b squared is an integer, given that a and b were integers. So we have a over a squared minus 5b squared. And then we have minus b over a squared minus 5b squared, and then this times root 5, because we still have that root 5 there. Okay, now this and this are both rational numbers. So a over a squared minus 5b squared and minus b over a squared minus 5b squared are both rational numbers. Okay, so we've shown here that a plus b root 5 has an inverse that's in this same set. All right, so let's move on and talk about our next field extension in our list. Q adjoin square root of 2 and square root of 3, and you can see I've got a tower of fields here that I'll use to talk about the Galwa group. Okay, but first let's talk about what this set is and why it's a field. Okay, so this is the set of, we have a plus b root 2 plus c root 3, such that a, b, and c are rational numbers. Okay, and we don't have to go any beyond that, because we have identities like root 2 squared is a rational number and root 3 squared is a rational number. I'm out of focus here, so I'll let this thing go back in focus. Okay, I think that's good for now. Maybe I had better keep my hand here. Okay, so inverses in here, they exist, right? But they're a bit more involved to calculate. So we'll just say that this adjoin root 2 and root 3 together with addition is an abelian group. Okay, and then we note that this with addition and multiplication is a commutative ring. And so we have 1 is our neutral or identity element of the multiplicative structure there. 0 is our 0 element or identity element of the abelian group. Multiplication commutes over addition, distributes over addition. So we have A times B plus C is A times B plus A times C, and that's the other way around too because it's commutative here. So is equal to B times A plus C times A, which is bracket B plus C times, on the right outside the bracket, A. Okay, so we have multiplication distributing over addition. Okay, now finally every element. So every element A plus B root 2 plus C root 3 has a multiplicative inverse, and that is in this same field. Okay, so it will be of this form as well, that inverse, right? But it'll be very involved for me to show you here by pen and paper, so I won't do that. Instead, what I'm going to do is move over here and talk about the tower of fields. Okay, which will correspond to the Galwa theory of that field. Okay, so we'll then also talk about the Galwa correspondence. Okay, so here I've represented that field. Here I have the base field Q, the underlying field. And then these three fields here are field extensions of Q, but they're subfields of this larger field Q adjoined to root 2 and root 3. Okay, so we have we have 3 subfields of this field. Now let's talk about the Galwa group of this over Q. Okay, now we've already said, I think we've already said, maybe not, that the degree of this extension is 4. Okay, so here is the minimum polynomial I need to describe the roots that are in this field. So x squared minus 2 times x squared minus 3. Now this has degree 4. Okay, so this extension is of degree 4 here. And that's equal to the number of automorphisms of the Galwa group. Okay, so here I've got the Galwa group drawn in the same way as a tower of groups. Okay, at the top I have the identity. Now, as an automorphism, this basically says send all of the elements of this field extension to themselves. Okay? Now, because I've said something about beta here, the identity together with beta as a subgroup of the full Galwa group, which is down here. So you notice the reverse order here in terms of subgroups and subfields over here, the reverse order. Okay, so beta is going to be the automorphism of this field that leaves Q adjoin root 2 fixed, meaning the elements of Q adjoin 2 are not sent anywhere. Okay, over here I've got listed the automorphisms of this field, and I see I should put, rather than iota, I'll just go with E, to meaning the automorphism that basically does nothing to your elements. Okay, so E basically sends x to x, so do nothing. Alpha sends root 2 to minus root 2 and minus root 2 to root 2 and leaves all of the other elements of this field fixed, as in it sends root 3 to root 3. Okay, so that's what alpha does. And the subgroup of this group here, consisting of just E and alpha, that will leave Q adjoin root 3 fixed. Okay, so we already said do nothing to root 3 here. In other words, send root 3 to root 3. Now beta, on the other hand, is the map that sends root 3 to minus root 3. It sends minus root 3 to root 3, but it leaves root 2 fixed, meaning that it would send root 2 to root 2. Okay, so it leaves this subfield of this field extension fixed. And then finally we have alpha beta, which sends root 2 to minus root 2. It sends root 3 to minus root 3. And it leaves Q fixed. Okay? So it corresponds to the subfield Q root 6 under the Galwa correspondence, which is what are we talking about. So the correspondence between these fields and these subgroups, right? These subfields and these subgroups. The full Galwa group corresponds to Q. Okay, so I'll just read out to you the fundamental theorem of Galwa theory, which says that, now this is a simplified form of this fundamental theorem, okay? So I'm basically trying to stick to the most simple parts of the theory to give you an overview here. If L extend K is Galwa, and this means that the number of automorphisms, so here we've got 4, is equal to the degree of the extension. Degree of the extension here is 4. Then there is a one-to-one correspondence between the normal subgroups, those are these, those are these here, the normal subgroups of the Galwa group, and the subfields that are intermediate between Q and the full L here, which is this one. Okay, now let's move on to talk about Q adjoin the cube root of 2. All right, now the minimum polynomial of this would be x cubed minus 2. So here we see that this this over Q is equal to 3. Okay, so that has degree 3. And I need 3 elements to represent this as a vector space over the underlying field Q here, right? So this is the dimension of the vector space Q adjoin the cube root of 2 with the underlying field 2. So you see that the elements of this field are of the form A plus B cube root of 2 plus C cube root of 2 squared, and this corresponds to the vector ABC, where A, B, and C are rational numbers. Now this Galwa group is basically the group of all automorphisms of the elements of this field. However, if you think of 1, the cube root of 2, and the cube root of 2 squared as, I guess, something like ABC, then there's a correspondence between the Galwa group of this field and the group of symmetries of the equilateral triangle, all right, which we know has 6 symmetries, or 6. We've got reflections about certain axes, rotations, right? So there's 6 such possible symmetries of this triangle here. So that's in one-to-one correspondence with the way that we can permute the roots here, as in 1, the cube root of 2 and the cube root of 2 squared. Okay, so we can do things to these roots, as in send them via an automorphism to this field in such a way that they correspond to the symmetry of this triangle here. Okay, but we know we have 6 of these. This has order 6, but this degree here, dimension of the vector space, is of dimension 3, and that is not equal to this 6, or the order of the Galwa group here. So we say that this is not a Galwa extension, and so we don't have the Galwa correspondence, because this is an if and only if statement down here. I haven't written the full statement, but it's an if and only if statement. So there's a one-to-one correspondence like we had here between the subgroups and the subfields if and only if you have a Galois extension. But here in the case of this cubic extension, I don't have a Galois extension there. So no one-to-one correspondence between the subfields and the normal subgroups of the Galois group over Q. Okay, again, this is an overview. There's a lot to unpack there, but I won't do that because I need to keep this as brief as possible for the purpose of this little course I'm doing for you. Okay, so next we're going to move on to talk about finite fields. And so here I'm going to move this page over and start talking about finite fields. Okay, so we've already talked about some finite rings, and one of those examples that we discussed was integers mod 3. So the representatives of this as a group and as a ring were 0, 1, and 2 modulo, or mod 3. Okay, so we had 0 being the additive identity. So I guess I'll put E plus is 0, and the multiplicative identity here is 1. Multiplication distributes over addition here, and every element of the multiplicative structure here that's non-zero has a multiplicative inverse. Okay, so these are 1 times 1 is 1, so the inverse of 1 multiplicatively is 1. Now also the inverse of 2, so 2 times 2 is 4, which is congruent to 1 mod 3, and so 2 is its own inverse in this structure. Okay, so every non-zero element of integers mod 3 has an inverse, and so this is a field. Okay, so let's briefly discuss this one now. We've already discussed that integers mod 6 together with addition and multiplication is a commutative ring. Right? But not every element, we learned in our last video, has an inverse. only 1 and 5 are invertible. And by inverse here, I mean multiplicative. Okay, and so integers mod n, the elements of that have an inverse multiplicatively whenever the GCD of the number here n is 6, with a, where a is just an element, if the GCD is 1, so A inverse exists in the ring integers mod n if and only if the GCD of n and a is equal to 1, right? So since we have, for example, GCD of 6 and 2 is 2, that's not equal to 1, so 2 inverse does not exist, right, in this structure. So 2 is not invertible. Similarly, 3 not invertible. For the same reason that the GCD of 6 and 3 is equal to 3, which is not 1. And 6 and 4 have a GCD of 2. So I'll just write that out. GCD 6 and 4 is equal to 2, and that's not equal to 1. So 4 inverse does not exist. But 1 and 5 do have inverses because the GCD of 6 and 5 is 1. GCD of 6 and 1 is 1. And 6 is the same as 0, so we don't need to consider 6. Okay, so this is not a field. Right, now there's a theorem that says, and I'll just write that in the box here, this is a field if and only if, IFF for if and only if n is a prime number. And by prime number I mean prime of the ring right? So prime as you would know it in the usual sense, but there's a higher notion of primes when you're referring to more general rings than just the integers here, right? As in, there are primes of the rational numbers, of the field of rational numbers adjoin root 5, right? So the generalizations of prime integers adjoin root 5. Okay, so we talked about this ring in the last video. Okay, but there's a notion of prime in this ring as well, which is not necessarily the same as the notion of prime in the ring of just plain integers. Okay, so we've seen an example of a ring that's not a field. So now let's talk about rings in which we have characteristic that's prime, so finite fields, but that are not necessarily, so I'll just write this out here. So an example of a finite field not of a prime order. Okay, so here we've got order 4, so 4 elements, but has prime characteristic. Okay, and remember the characteristic of the field here. So in this case, this element is acting as the number 1. Okay, number 1 there. So if we add this to itself, so 0, 1 plus 0, 1, okay, if we just look in our Cayley table here, we get 0, 0 here. Okay, now 2 of those were required in order to do that, but 2 is not equal to 0 there. And so we have a characteristic, sorry, I should say not equal to 0. So we have a characteristic of the field F4 is equal to 2 here, right? So the characteristic here is prime when you've got a finite field. Okay, so here I've got a Cayley table for addition, a Cayley table for multiplication in this field. So the elements are the numbers in binary, so 0 and 1. So they're elements of F2, but they're pairs because we've got a Cartesian product here. Okay, I'm just saying that there's an isomorphism between this field and this, just so we can see something that we've already studied. Now here on the left we've got what we call the Vir group. So Vir in German meaning 4. Okay, but here we've got the multiplicative structure of this, and soon we're going to see this from another point of view in terms of polynomials. Okay, so here we have defined 0, 1 times 0, 1 is 0, 1. 0, 1 times 1, 0 is 1, 0. So we can see that this is acting as our neutral or identity element of the multiplicative structure here. And then let's just take another example. 1, 0 times 1, 1 is 0, 1. So these two, 1, 0 and 1, 1, are multiplicative inverses because we've got this one here being the multiplicative identity element of this multiplicative structure here. So let's just note that 1, 0 inverse multiplicatively is the element that we multiply by in order to give us the identity element. So this is 1, 1 here, because the product of that, of 1, 0 and 1, 1 is the identity element multiplicatively, which is this one right here. Okay, but this here I want to point out that multiplication distributes over addition. So let's just do this. So if we add these first, we have 1, 0 times, adding these, we have 1. 1 plus 1 gives 0. Okay, now if we look in our multiplication table here, 1, 0 times 1, 0. 1, 0 times 1, 0 is 1, 1. Okay, and now the other way around, or sorry, distributing this over addition. Okay, so 1, 0 times 0, 1 plus 1, 0 times 1, 1 is equal to, so 1, 0 times 0, 1, 1, 0, 0, 1, so we've got 1, 0 there, and then we're adding 1, 0 times 1, 1, which is 0, 1. Okay, now adding those two together, we have 1, 1, which agrees with what we have right here, if we add those first and then multiplied. Okay, so we see then that multiplication distributes over addition, and so that tells us that F2 cross F2 together with addition and multiplication is a ring, We've checked the conditions for which this is a ring. But it's actually commutative too, because if you look at this Cayley table here, you can see symmetry about the diagonal. Okay, and so we see that AB is equal to BA in this multiplicative structure. So it's also commutative. Okay, and we see then that we have a commutative ring. And now our final thing to check to verify that we have a field structure here is that every element of this multiplicative structure, excluding 0, so just this little 3 by 3 box, every element here has a multiplicative inverse that gives us this 0, 1, which is our one element. Okay, so we're looking, do we have 0, 1 in every row and every column of this little 3 by 3 section, excluding 0? Okay, we have 0, 1 there, we have 0, 1 there, and we have 0, 1 there. So yes, in every row and every column of the section consisting of excluding the row and the column, that 0, 0 is in, which is our 0 element there. So that tells us that every element has an inverse. Okay, every non-zero element of so these are the same, but I've started to write integers mod 2, so that's okay because these two things are the same in this case. Every non-zero element of this has an inverse, and that by that I mean multiplicative inverse. All right, so having discussed this field, we note that this whoops, hang on, I want a comma there, didn't want that. So this as a ring is not isomorphic to the ring integers mod 4 with addition and multiplication. So as rings, these two are not isomorphic, right? And so I don't use this Z here when I talk about the field. So I can put F subscript 4 to talk about the field integers mod 2 cross integers mod 2. So these two as fields are isomorphic, right? But you notice here I've used a Z4 here and an F4 here. So this refers to the ring, this refers to the field. Okay? So remember, we also have, now let's see, where do I? Let's see if I can find the page from the last recording that I did, where I had the Cayley table of integers mod 4. Hopefully I have it. So let's see if I can find this. Okay, it's on this page. Except it looks like I haven't written down the multiplicative Cayley table for integers mod 4 as a ring. Okay, so I'll have to leave that there then. All right, so moving on. So our next topic is that there's another way of looking at this field with 4 elements in it, and it's in terms of polynomials. Okay, which brings us to this major important result. If n is greater than 1, then the field, the finite field with p to the power of n elements, and we also call this Galwa field, or GFP to the n, So I'll just write that 2 because it's another notation for the same thing. GF P to the power of n. Okay, is another word for this. But this is isomorphic, so has the same algebraic structure as the finite field of P elements adjoin X. So all polynomials where the coefficients are in this finite field of P elements. And then you basically reduce this. So it's like you reduce this modulo a particular polynomial. So that's the basic, I guess, loose way of describing what's going on here. You're reducing modulo a polynomial. So, for example, and this has to be irreducible, right? So for some f of x that is irreducible in this ring of polynomials here. Okay, so for example, in the case of the finite field of 4 elements, this is isomorphic by this result to integers mod 2 adjoin x, so the ring of all polynomials where the coefficients are integers mod 2, so 0 and 1, for example, modulo f, where f is x squared plus x plus 1. Now this is irreducible in that in the field of integers mod 2. Okay, so we're going to see here another example of an isomorphism in terms of polynomial rings. Okay, as another example, the finite field with 9 elements is isomorphic to the ring f3 adjoin x modulo f of x, where f of x is x squared plus 1. Okay, but I'll first look at this example and then we'll refer back to the other view of the same field. Okay, so this consists of, so remember what these are here. These are polynomials a plus bx plus cx squared plus dx cubed and so on, where these coefficients here of the powers of x belong to the finite field with 2 elements in it. Okay, and we note that we're treating x squared plus x plus 1 as if it's 0 here. So we can add multiples of this to reduce, just like, say, when you reduce modulo 12, think about 1500 hours. 1500 hours is the same as 3 p.m. So we're taking out multiples of 12 there. So just like this, we take out multiples of x squared plus x plus 1. Okay, now what I've done here is I've listed a few of the elements of this polynomial ring here. So we've got 0, we have 1, we have x, we have 1 plus x, we have x squared, we have 1 plus x squared, x plus x squared, 1 plus x squared. And then we have cubic terms as well, but since we can treat this as 0 in the ring, we have far fewer. And I'll just show you that we don't even need the squares here, right? Because, so we have 0, we have 1, we have x, we have 1 plus x. And so these are our representatives here that I've got set out in our Cayley table, but I'm going to show you that x squared is one of these 4, okay, when we treat this as 0. So we have x squared is equal to x squared plus x plus 1. And now, because x squared plus x squared is 2x squared, and 2 is congruent to 0 mod 2, so this then is the same as x plus 1. Okay, so wherever we have x squared, we can replace it with x plus 1. Now, similarly, 1 plus x squared, we know that x squared is x plus 1, so this is equal to 1 plus x plus 1. And so that's 2 plus x, but 2 is congruent to 0 mod 2, so this is just x. So this one here. Okay, now x plus x squared, well, we've got that this is equal to x plus 1, which is equal to 2x plus 1, but 2 is congruent to 0. So reducing that coefficient mod 2, we see that this is just the number 1. Okay, and we've already said here that x squared plus x plus 1 is 0, so this is just 0. Okay, so we actually have just these 4 elements here in this ring when we reduce it modulo x squared plus x plus 1. Okay, so now let's fill out this multiplication table. So 0 times 0 is 0, 0 times 1 is 0, 0 times x is 0, 0 times 1 plus x is 0, and the same the other way around. 1 times 0 is 0, x times 0 is 0, and 1 plus x times 0 is 0. Okay, 1 times 1 is 1. 1 times x is x. 1 times 1 plus x is 1 plus x. And x times 1 is x. 1 plus x times 1 is 1 plus x. X times x is x squared, but we've seen that x squared is x plus 1. Okay, which is 1 plus x. So I should probably put this the other way around, just so that it's more recognizable as the same element. Okay, x times 1 plus x is x plus x squared, which we've learned is the number 1. And the same the other way around. And now finally, 1 plus x times 1 plus x, let's just calculate this somewhere here. So that's x plus 1 all squared, which is x squared plus 2x plus 1. Which is, when we basically subtract this, we just find that that's x. Okay, so we have x there. Now that we have that, notice that we have 1 in every row and every column, excluding the products where we had to multiply by 0. And finally, there's a correspondence here between this multiplicative table here, because we now have a dictionary, right, where 1 plus x is 1, 1, and then x is 1, 0 in our dictionary, as in our correspondence between this view of that field and 0, 1 corresponds to 1, and 0 corresponds to 0, 0. Okay, so we have a rule for associating these in this polynomial ring modulo x squared plus x plus 1. And this structure is a finite field, we see, because every element has an inverse. The inverse of 1 plus x is x. The inverse of 1 is 1. And that's everything, right? Okay. And so you can see that there's a correspondence in these tables here. If you perform these replacements here, replacing 0, 0 with 0, replacing 0, 1 with 1, replacing 1, 0 with x, everywhere in this table you'll actually get this table. Okay, so what we have then is a field isomorphism between this and this field here. Okay, so whenever you have a finite field, you can view it as a polynomial ring modulo some irreducible polynomial that is in that ring. Okay, so now we could do the same here with F9 or GF9. Right? So in the other way of writing that, GF9, we can view that with these 9 elements of F3 adjoin X, as in that ring. And now to find these, well, what I can do is I can write the numbers 0 to 8, not in binary, but in base 3. Okay, so I count, this is 0, then I have 1 in base 3. Then this would be the number 2 in base 3, and 1, 0 is the number 3 in base 3. This is the number 4 in base 3, 5 in base 3, and so on. And this down here is 2 times 3 plus 2, right? But it's probably the other way around here. It's a little bit confusing as to the order. It should be in reverse order. So this is 8. Okay, so I count in binary from 0 to 9 minus 1 in order to be sure I've listed all of the elements of the Cartesian product Z mod 3 cross Z mod 3. Okay, so I've got 9 elements. And then I find a particular polynomial here. So in this case, x squared plus 1 is irreducible. So just write IRR for irreducible in F3 adjoin x. So that is polynomials with coefficients in F3 that could have as high a degree as you like here, right? So it could have degree 17, for example, but I can always reduce those if I'm treating this as 0 here. Okay, so let's just give a little example here. So x squared plus 2x plus 1. Okay, what is that when I reduce mod this? So I would take away this one and this one, right? Because I can subtract this polynomial here, and I just call that the same as 2x. Modulo x squared plus 2x plus 1. Okay, so in other words, this one. And I can do that to all of these. Okay, I'll just show you the correspondence here. So in this order, 1, 2 would correspond to 1 plus. Actually, is that the right order? 2x. So yeah, this is corresponding to 1 plus, or x plus 2 there. Okay, this one corresponds to x plus 1. 2, 0 corresponds to 2x, and so on and so on. So I've got them listed here in that exact correspondence for obtaining those. Okay, and I'll let you fill out this Cayley table here, because we're going to have 9 times 9 is 81 entries in the product here, in all of the products. Okay, and that would take me forever to fill out. So you can just pause the video here, fill this out, reducing modulo x squared plus 1, right? And so this is the Galwa field with 9 elements. Okay, and so briefly, I'll talk about the so-called Frobenius Automorphism. So it's an automorphism of the finite field with p to the power of n elements. And here think of n as a number, or a natural number greater than 1. Okay, and the map here in the automorphism sends x to the power of p, but it's going to leave fp fixed. Okay, and so there are Galwa groups, fpn over fp, which is a group of automorphisms. Okay, that leave this underlying field fixed, and so they're of this form. Now, there are a couple of other things, well, this here, for example, that makes this possible. So, This is called the freshman exponentiation because in your first year of, say, university, or even your first year of high school, you might imagine that x plus y to the power of some number is just x to the power of n plus y to the power of n, which is in general not true for algebraic expressions, but in this finite field of p to the power of n elements, this does hold true, right? Because when you expand this, so if you just think about this algebraic expansion here, this is equal to x to the power of p, and then you have plus p x to the power of p minus 1 y to the 1, and then you have binomial p choose 2 times x to the power of p minus 2 times y to the power of 2, and then plus and so on, right? We have, I guess, p choose r, x to the power of p minus r, y to the power of r, and then plus dot dot dot. The last one is y to the power of p. But in FP, p is congruent to 0 mod p, right? And so all of these coefficients have a p in them. So p choose r, for example, is congruent to 0 mod p. In other words, p divides this binomial symbol here, right? And so this one is congruent to x to the power of p plus y to the power of p modulo p, and in fact even modulo p to the power of n. And so that's why we have this identity in this Galwa field of p to the n elements, or the finite field of p to the n elements. Okay, and this makes this automorphism an automorphism here that leaves the underlying field here fixed. Okay, and so you can draw towers of fields, and there is a Galwa correspondence here for finite fields also. All right, so I think I'll stop here with fields, and in the next video I'll be talking about probably the Euclidean algorithm. So the next few videos will be on elementary number theory. Thank you.